Hello and welcome back to the YOLO series. This is the second part to the video I made about PP-YOLO, and in this video we're going to cover the subsequent versions of PP-YOLO, which are PP-YOLOv2 and PP-YOLOE. But before we move on, make sure you like, share, and subscribe to my YouTube channel and ring that notification bell so you never miss another episode. So to recap, last time we covered that Baidu started out creating their own flavor of the YOLO object detector that is based on the already popular YOLOv3, for which they branded it as PP-YOLO. So PP-YOLO took the YOLOv3 network and made it an iterative improvements in training and architecture by adding a resonant backbone, a drop block regularization, an IOU loss, grid sensitivity, matrix NMS, chord conv, SPP layers, and a better ImageNet pre-training checkpoint. So in April 2021, Baidu released their second iteration of PP-YOLO called PP-YOLOv2. So, okay, the competition is getting heated now. According to their paper called PP-YOLOv2, a practical object detector, they have mentioned that they had surpassed existing object detectors like YOLOv4 CSP and YOLOv5L with the same amount of parameters. So now let's compare the difference between the YOLOv2 and PP-YOLOv2 models, since the object detector PP-YOLOv2 improves upon YOLOv2 in several ways. The first one is by introducing a path aggregation network. The FPN, as we talked about in a previous video, includes a path aggregation network which was introduced in the YOLOv4 architecture to create the bottom-up pathways. So this neck part of the network was also implemented in the PP-YOLOv2 model, which was a modification that was made on the YOLOv2 architecture. As you remember, in the YOLOv2 we used a feature pyramid network and not a path aggregation network on the neck part of the model. The second modification that they made was that they used a ResNet50 backbone with deformable convolution on the backbone of the network. The third modification was implemented on the head part of the network. They used a lightweight IOU-aware height, and the authors tuned YOLO's loss function to make it more aware of the overlap between bounding boxes. Fourth, they added the mesh activation function to the neck of their object detector, but not to the backbone, preferring to use the ImageNet pre-trained backbone. The fifth is the input size, and they increase the image input size by drawing uniformly across different input sizes. The input volume has increased from the previous versions. And sixth, they use a soft label. Soft label format is used to calculate an IOU-aware branch. So what is the significance of the PP-YOLO version 2? The main significance of PP-YOLOv2 is that it primarily aims to combine multiple already used techniques that rarely increase the number of model parameters and flops to improve the detector's accuracy as much as possible while keeping the speed nearly the same. So they wanted to maintain the speed and increase the detector's accuracy as much as possible. And the term flops here describes how many floating point operations a computing device can carry out in a single second. So flops is a metric that's commonly used in computer science in order to measure the amount of operations, floating point operations that are computed by using a certain computing device. And finally, let's see the results from this new version of PP-YOLO. So by implementing the techniques that I've mentioned before, The authors compare their newly forged PP-YOLOv2 against other similar object detection models in deployment conditions. And for the evaluation, they used the COCO dataset. And as you can see from the graph on the left side, we see the mean average precision on the y-axis and the frames per second on the x-axis. And inference time is also measured as the time it takes to infer against a single frame on a Tesla V100 GPU. And inference speeds are measured both with and without the TensorRT acceleration. And here we can see that the orange lines indicate the newly introduced models, the PP-YOLOv2 model, by using a ResNet 50 backbone and another variant which uses a ResNet 101 as a backbone. And here we also have the original PP-YOLO version 1, which is indicated on the line here. And the two subsequent models are mentioned here. And as you can see, they are located further upwards on the graph, which means that they have a higher mean average precision compared to other models. And here we have another baseline model, which is the YOLOv5 model, and here is the YOLOv3 model. In PP-YOLOv2, we increase the PP performance of YOLOs from 45.9% mean average precision to 49.5 mean average precision by combining several efficient enhancements. And PP-YOLOv2 operates at 68.9 frames per second with 640 input size. And the training batch size has increased from 64 to 192. And the DarkNet 53 backbone of YOLOv3 has been replaced with a ResNet backbone, and the mini batch size of 24 was used on 8 GPUs. Now that we have discussed the significance of PP-YOLOv2 and the results, let's finalize by mentioning the issues associated with the PP-YOLOv2 model. Even though PP-YOLOv2 has overcome a lot of problems faced in other object detection models, there are some minor issues with it. Because each grid can only detect one object, performance suffers when there are clusters of little objects. These clusters of many tiny objects fall under many grids, making the decision more difficult. Because the ratio of the bounding box is entirely learned from data, and the main error of YOLO is from the localization error. And PP-YOLOv2 makes errors on the uncommon ratio of the bounding box. So we have two issues with the PP-YOLOv2 model. The first one is the localization error, and the second one is the uncommon ratio of the bounding box, which are the two mentioned disadvantages of this model. Now enter PP-YOLOE, which is the third and final version of PP-YOLO. Now, I don't know whether it was the pandemic or the change of management, but why did they call it YOLOE? Couldn't they not have called it something like PP-YOLOv3? Was it because of all of the newer models of YOLO were being called YOLOX, YOLOR, YOLOP? They were using letters instead of numbers to describe new versions? Well, we don't have an answer for that. The only reasonable explanation is that maybe PP-YOLOv3 would have been confused with the YOLOv3 model in terms of search engine optimization. I don't know honestly, but they named it PP-YOLOE, which might stand for an extension for the PP-YOLO model. Anyways, on the 2nd of April 2022, Baidu released their subsequent paper YOLOE, an evolved version of YOLO. So maybe here E stands for evolved version of YOLO, which is said to be an industrial state-of-the-art object detector with high performance and friendly deployment. They state that they were inspired by the YOLOx model for its anchor-free method, equipped with a dynamic label assignment to improve the performance of the detector, which they claim has significantly outperformed YOLOv5 in terms of precision. Knowing this, they further optimized their previous work in PP-YOLOv2. As we have mentioned before, the PP-YOLO and PP-YOLOv2 model do not introduce any novel techniques which weren't mentioned in the previous versions of YOLO. They just slightly modified the backbone and used different types of training techniques in order to improve the performance of the model. But PP-YOLOe is slightly different from the previous versions of PP-YOLO because it also introduced some novel techniques. And in the video about YOLOx, we mentioned that it is an anchor-free method, and they also used this anchor-free method in order to enhance the performance of the PP-YOLOv2 model. Similar to YOLOv3, PP-YOLOv2 only assigns one anchor box for each ground truth object. This mechanism, however, requires a number of extra hyperparameters and relies heavily on handcrafted designs that may not generalize well when trained on other datasets. So, the PP-YOLOv2 only uses one anchor box for each ground truth object. And what it does is that it increases the number of hyperparameters that were initially planned for and relies heavily on handcrafted design, which will not generalize well when it's being trained with different types of datasets. Now, let's talk about some of the improvements that they implemented on the PP-YOLOv2 model in order to create the newly evolved PP-YOLO model. To address this issue, the Baidu researchers introduced an anchor-free method to PP-YOLOv2 that tiles one anchor point on each pixel and sets upper and lower bounds for detection heads to assign ground truths to a corresponding feature map. So we have already mentioned that they have implemented an anchor-free method to the PP-YOLOv2 model, and it tiles one anchor point on each pixel, and it sets like a upper and lower bounds for the detection heads, which are located on the in the final stages of the model, to assign ground truths to a corresponding feature map. And the center of the bounding box can then be calculated to select the closest pixel as positive samples. So when these anchor points are associated with each pixel, and the closest pixels to the center of the bounding box, the ground truth bounding box, were considered as positive samples, and the rest are considered as negative samples. And a 4D vector is also predicted for regression, with modifications resulting in slight model speedups and precision drops. One of the major improvements, and which are considered to be novel, is the new repres block that they introduced in the backbone and neck of the network to build what is known as a CSP RepResNet backbone with one stem composed of 3 convolution layers and 4 subsequent stages stacked by repres block. So as you can see, this is a simplified 3 block, and we have 2 convolutions here, 3 by 3 and 1 by 1. And we have another branch, which is a 3 by 3 convolution. And here we have the original feature maps without performing any kind of convolutions. And we concatenate them together before we move on to the next stage. And on B, we can see that the repres block, a single repres block, which was implemented only during the training phase. And here we can see that we have two 3x3 convolutions, and there is also a 1x1 convolution. Here the original feature map was sent directly below, and on the second branch we perform a 3x3 convolution. Then we divide it into two branches, and we follow that 3x3 convolution by another 3x3 convolution and a 1x1 convolution. Then we add them together. This is an element-wise addition operation, and here also we also add with original feature map. And this is another repres block, but it was implemented during the inference time, during the inference stage. And here we also have two branches, and we just implement two 3x3 convolutions without implementing the 1x1 convolution. And we perform element-wise addition operation here. And finally, by composing n times of this initial repres block here, which in their case is 4 subsequent repres blocks. Maybe here we can implement it 4 times. So what they did was using the CSP, the cross-stage partial connections were implemented in order to reduce the number of parameters and the computational burden. And following PP-YOLOv2, the team also builds a neck with the repres block and the CSP repres stage. So after they proposed this new technique, they implemented it both on the backbone and the neck of the model. And as you can see, when the cross-stage partial network was used in PP-YOLO, here we perform a 1x1 convolution first, and we divide it into two branches. And the first one, on the first path, we perform n number of res blocks, and here we have a concatenation after performing a 1x1 convolution on the other branch. And here we have AAC, and then finally we have a 1x1 convolution. Besides implementing new novel techniques or convolutions on the backbone and neck part of the model, the researchers also use task alignment learning, which is known as TAL, which was proposed by Fung et al. In 2021 to replace label assignment, which also gave them a boost in terms of average precision. It increased to 0.9% average precision improvement and pushes the overall AP to 50.4%. So as you can see from the figure on the left side, we have the PP-YOLOv2 baseline model, and here we have the mean average precision on the second column, the number of parameters, the G-flops, latency, and frames per second. As you can see, the baseline model has a mean average precision of 49.1%. When they first implemented the first improvement, which was using an anchor-free head, the mean average precision actually dropped by 0.3. And here we have a CSP represnet, which we talked about in the previous slide, and they got an improvement in terms of the mean average precision of 0.7. And after implementing this task alignment learning for label assignment, they also got an improvement of 0.9. And finally, we will talk about the AT head, which also gave them an improvement of 0.5. So the final improvement that we haven't mentioned is the ET head. So finally, to solve the task conflict between classification and localization in object detection, the researchers use effective squeeze and extraction to replace the layer attention in conventional task-aligned one-stage object detection, simplifies alignment of classification branch to shortcuts, and replace the alignment of regression branches with a distribution focal loss layer. And additional modifications to the resulting efficient task-aligned head, ET head, further improves performance. So the ET head is just efficient task-aligned head, and they implemented what is known as an effective squeeze and extraction to replace the layer attention model. So I think we have already talked about squeeze and excitation models, which were one of the techniques in order to use attention uh, models in order to implement attention in visual models. And they also implemented it in the conventional task-aligned one-stage object detection to improve the performance. So this is just a fancy name in order to describe this process. And it gave them a performance boost of 0.5. Finally, let's see the results from the new PP-YOLOe model. The researchers performed evaluation experiments on the MS-COCO 2017 training set, comparing the proposed PP-YOLOe with state-of-the-art object detectors such as YOLOx, YOLOv2, and efficient DET. So whenever you come up with new novel techniques to improve the performance of the model, you have to compare with other baseline models. And they have already described the results by using this table. And here we have the YOLOv3 and YOLOv4 models. Here we have the Google's efficient DET detection network. This is the PP-YOLO version 1, and this is the PP-YOLOv2, YOLOv5 models, YOLOx models, and the PP-YOLOe, the newly enhanced or evolved PP-YOLO model. And these are the backbones which were implemented. As you can see here, all of the backbones that were used implement the CSP repres technique. And the previous PP-YOLOv2 and PP-YOLOv1 just use the ResNet 50 and ResNet 101 as a backbone. And here we can see the average precision results on different scales or mean IRUs. So in the test, PP-YOLOe1, which is the first variant, scored 51.4% mean average precision with 640 by 640 resolution at a speed of 78.1 frames per second, an AP improvement of 1.9% and a 13.35% speed up compared to PP-YOLOv2 model, and a 1.3% AP improvement and 24.96% speed up compared to YOLOx model. So they proved that they had gained a performance improvement in terms of mean average precision, and the proposed model's inference speed reached around 149.2 frames per second with tensor RT FP16 precision. So they also got a speed up and also an improvement in terms of average precision. Overall, PP-YOLOe is shown to be a high-performance object detector. The model series can only smoothly transition to deployment thanks to support from the Paddle deep learning framework. The team hopes their design updates and encouraging results can inspire developers and researchers working in object detection. And from the figure on the left side, we can see the results from the different versions of PP-YOLO and also some baseline models like YOLOx and YOLOv5. On the y-axis, we have, as usual, the mean average precision, and we have the frames per second on the x-axis. As you can see, the PP-YOLOe model is always on top, which is a good sign because its mean average precision will also be high. And we have the this is the YOLOv5 model, and this is the results from the YOLOx model. and this is the PP-YOLOv2 model, and this is, the blue line indicates the first version of PP-YOLO. That's all for this video, and don't forget to subscribe to my YouTube channel.